Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Hey, today we want to talk about the topic of potential energy. Potential energy. Now, you've probably learned about this in middle school even. There was potential and kinetic energy, and we're going to focus on potential energy. Now, it turns out that there are a variety of different types of potential energy. We're going to focus on several of them, but the gravitational potential energy. So if I lift up an object, so I lift up my calculator, by giving it additional height, I'm giving it gravitational potential energy. We've also got spring potential energy. And we've also got, so like if I have a spring and it's coiled, right, I pressed it down, then it can spring up, and that would be potential energy. And then I can also have chemical potential energy. So if you're having a candy bar, it's not actually being translated into motion yet, like kinetic energy. It's just sitting in the chemical bonds. And you've also got nuclear potential energy. So what is the idea of what is potential energy? I think that's the important thing to ask ourselves. Potential energy is the ability of an object or a system to create motion. So if I have a candy bar in my hand, I could be translated into motion, me doing a run, right? So it's that's the chemical potential energy. The spring could cause, if I have a ball on the top right here, right, can cause the ball to spring upward. And of course, by me lifting the pin up to a height, it has the ability to fall. Oops, drop it everywhere. And that is what potential energy is. Now, we got the concept of kinetic energy in the last video, is that, of course, is the energy of motion. Potential energy is a weird concept because it isn't actually doing anything, it just could, hence the word potential energy. Now, in this video and in this class, for all intents and purposes, we're going to focus on gravitational and spring potential energy, chemical and nuclear. Probably here, at least at our school, this is a topic you would probably cover most likely in an AP chemistry course. It's pretty cool, and nuclear is really fascinating, but go further and you can learn about those types of potential energy. So let's first talk about gravitational potential energy. And of course, it has a symbol, and the symbol doesn't make a lot of sense in my opinion, but it's a big letter U. I didn't draw that very well, did I? A big letter U. And it'd be U sub G. So potential energy has the symbol U. The G stands for the potential energy of gravity, and it is very simply equal to just M times G times H. Mass, and G is the acceleration of gravity on the Earth, 9.8 usually. On some other planet, it might be a different number. And the height is how much height you raise it. So if I take the pen, all right, so let's just do a problem. Let's say that I have a table here. And on that table, I have a book. And I'm going to take this book and put it up on this shelf. All right. And let's say that this is at 1 meter. And this is at 3 meters, much higher, let's say. And so your change in height, or delta H, would be 2 meters. And if I know the mass of the object, say the mass of the object is 2 kilograms, then what you would do is you would take 2 kilograms times 9.8 times 2 meters. That's how much increase in potential energy it has when it's moved to the higher place on the bookshelf. It's really that simple. It's not terribly difficult. And the units, of course, will be what? It will be a joule. Now, the word joule, by the way, we haven't said this, but joule we want to say out loud because it takes energy to say joule. So we should shout joule when we speak in class. How many joules? Silly, but hopefully that will help you remember. And it's a weird unit, joule, named after Mr. Joule, I guess, right? Now let's talk about a weird type of question that's often asked in a physics problem set, textbook deal thing. And that, you'll often see a question that asks something this. They'll say this. You might ask, like, how much work does gravity do on the book? As we rose this, by the way, we didn't calculate what this was. We did. It's going to be 2 times the acceleration of gravity. I'm just going to round it up to 9.8, call it 10, times 2. So 10 times 2 is 20. 20 times 2 is, that'd be 40 joules. So the book increases its energy, its potential energy by 40 joules. But how much work does gravity do on it? Now, if you think about it, gravity is always pushing down. So if I raise the book up 40 joules, I give it 40 more joules of work, gravity has lost that 40 joules. So the answer to our problem from over here would be negative 40 joules. I mean, really, the reality is downward is negative, because that's what gravity is pushing down, right? And upward is positive. That's really the way to think about it. And we've thought that through before. Is negative 9.8 is, or you like think of the gravity as negative 9.8, and that would be that question. So it's going to create some weird sign things, but it's not that hard to figure out. And the second kind of potential energy that we're going to talk about in this class is the U spring. So spring, and that equation is a little bit weird. It's 1/2 kx squared. Now, if you recall K is the spring constant. And that's in newtons per meter. And X is how much you compress the spring. So it could be in the X direction, it could be in the Y direction, or whatever. And so if I have a spring, right, and then I compress it, and so let's say that the length of the spring is 1 meter, and then I compress the spring to a much tighter thing, and I compress it to 1/2 meter, then it's the change in the X, you probably should say delta X. The change in the X is 1 minus 0.5, and so, and if I knew the constant, let's say the constant is 1,000 Newton per meter, then if I were to compress that spring, then the potential energy in joules, right, would be 1/2 times 1,000 times 0.5 squared. So what would that come out to, just for funsies here? So I'm typing in 0.5 times 1,000 times 0.5 squared. This would be 125 joules. So that would be the amount of energy, potential energy, if we were to compress this spring down to 1/2 of its normal distance. This can also lead to other types of questions, but basically you've got two big equations. The U of spring, and then the U of gravity is just M times G times H. Houston, we don't have a problem. We will see you in class.